Yeah, thank you for the chances. It's really interesting for us to learn from everyone's nice work here. We are just new in this, let's say, in this business and more toward the direction of the computational chemistry side. So today I'm going to share with you something that we are trying to do remotely related to drug in a sense, as to what we learned from optimizing the beta-lactam force field parameters using the force field toolkit or FFTK. Yeah, right. So this why we start to do that is because we are interested in the MRSA, in the antibiotic resistance. So MRSA, the methicillin resistance Staphylococcus aureus, is a multi-drug resistant bacterium. In particular, it is resistant to almost all beta-lactam antibiotics. So the reason that it can do so is that first, it can produce the penicillinase, which is an enzyme that can decompose the penicillin kind of antibiotics. So penicillin G, for instance, it can decompose it. But this is not the most important. The most crucial part is that this bacteria can also produce a so-called penicillin binding protein 2A, PBP2A, to replace the original PBP that is vulnerable to the or sensible to the beta-lactam antibiotics. So for these cases, the PBP2A basically it has a very low affinity to most of the beta-lactams, so the usual beta-lactam doesn't bind to it so easily and then cannot inhibit it. So that is why it would have a very high resistance, except for one drug called ceftaroline. So ceftaroline is an active drug against MRSA. That means it cannot be decomposed by penicillinase and it can bind to PBP2A. So the reason that why it can bind to PBP2A was not very clear until the 2013. Professor Mobashiri, their group actually crystallized this PBP2A with the ceftaroline. So basically they have a complex crystal structure, and that they found that the first ceftaroline, it binds at the transpeptidase domain of the PBP2A, is where the usual beta-lactam is supposed to bind to inhibit the function of this protein. And interestingly, they find that at the 60 angstrom away, there is another ligand, another ceftaroline binds at the so-called allosteric domain. So based on this discovery, they think that the binding of this ceftaroline at the allosteric domain somehow promotes or activate the transpeptidase domain, this active site, and promotes the other ceftarolines binding at the active site. And so based on this picture, then people start to think, how can we design allosteric drug such that we can promote or say enable the usual beta-lactams to bind at this transpeptidase domain. However, if you look into the crystal structure, you'll find something interesting. The first thing is the second ceftaroline at the allosteric domain. It binds at rather surface. So basically, there is this is just a bad picture that shows in the literature. It looks like the second ceftaroline was somehow clapped by the protein, but actually it's not. It's actually somehow bind on the surface. So the first thing one would try to answer is, how does this the first thing one would try to ask is, how does this ceftaroline bind to the allosteric site? Can we somehow understand what is the important residue that interact with these ceftarolines through the MD simulations? So we try to do the MD simulations, but back to them, we first try with the CHARM36 force field for protein, and then we use the ligand force field, that is the CGNFF, which is the Chang general force field that goes together with this force field, CHARM36. So the idea is that we start from using the CGNFF web server and upload the ligand PDB and then get the parameters, and then wanted to use it for simulation. And the thing is, if you look into the parameters you get, actually CGNFF web server will generate an initial guess for your parameters with the penalties to indicate whether this initial guess is good. Yeah, the thing is, if you look into the penalty and you analyze it a bit, you find that most of the parameters, at least half, have high penalty and they require the further optimization. So, of course, in this field, many people would just accept that you use the default from the CGNFF web server without optimization. However, we would still wanted to have a better, let's say, description of the ligand. So we decided to carry out the optimization of the force field. So as you can see, this is a very complicated ligand. It's difficult to do the whole ligand in one step. So we decide to truncate it into three parts. The first and the most important part is the middle part, this caffeine group. So basically it's like this. So basically, if you look into the caffeine group, you still find they have a lot of penalty. Basically, a lot of parameters with high penalties and require optimization. And actually, not only caffeine, if you look into pinam, which is the core for the penicillin and the methicillin, they also have the high penalties. More than half of the parameters require validation. So we begin with Pinan, which is an easier example in these cases. So we use the force field toolkit to do that. The idea is after you get the PDB file and get the CGNF parameters, what you are going to do is you start by performing the geometry optimization through content calculation. So we do a content on geometry optimization and find the global minimum of the ligand of the structure. And then once you optimize it, the next thing we do is to place the water around the ligand and then try to calculate the water interaction with the ligand. And through this quantum calculation, we can try to fit the charge of the atoms. So we do, then you can have this charge optimization. And after that, the optimized geometry of the ligand, you can use it to calculate basically the Hessian matrix. So from the Hessian matrix, you can calculate the distortion energy, and then you can fit your angle and bump parameters to this distortion energy, build it based on the Hessian matrix, and then they give you the bump and angle parameters. And then the last step in this whole workflow is to use dihedral scan. So basically for each single bond, you can rotate it and then calculate its quantum potential, and then you try to fit the parameters to reproduce the quantum potential, and then you can get the final parameter file for simulation. So when we do that, so in the beginning, we just follow whatever the tutorial tells us to do and try to fit. So this is the naive fitting. You can see the quantum and the fitting result. The fitting result is not perfect, but more or less follow the trend of the quantum potential. But if you just took these parameters for simulation for 15 nanosecond MD, you can find that basically the major conformation from the MD simulation differs from the quantum geometry optimization very much. So the MSD is till 0.6 Armstrong. So this is definitely not a good way to do it. So at this point, the student will start to ask, are we doing the right thing? Well, I still think that it's the right thing to try to optimize the ligand force field, because you can see with the bad force field, your MD simulation will just simply capture a different ligand conformation. And the question here should be, how can we do the things right? So if you look back to the bad structure, the first thing we wanted to know is which parameter actually make it is the bad one that make this very strange conformation in the MD simulation. So is it because we have bad parameters from the 4-member ring, or because we have the bad parameters from the 5-member ring? In fact, if you directly do this fused ring, it's very difficult to judge which part actually give you the trouble. So the easiest way for us is actually go back to the simplest β-lactam, which is this mono-lactam only has a one single 4-member ring. And if we could, with this protocol, with this FFTK, if we could reproduce, if we can generate the parameters that can reproduce the quantum geometry optimization, then we can use the same protocol or apply it for the other β-lactams, right? So with this idea in mind, we go back to the mono-lactam, and then this is the parameters obtained from the CGNFF. In fact, the CGNFF database has, let's say, validation. They directly parameterized this monobar for you, so that's why you don't see any penalty in these cases. However, if you look into the angle of parameters of the angle given by the CGNFF, you will find that, okay, the quantum optimized geometry give you the angle which is around 90 for the full angle, because the scene is like forming a plane. But CGNFF parameters give us a value that is all way above 100, which is completely off. So now if you think about how the parameters for the angle abound are fitted, you realize that it's based on a Hessian matrix, and you assume that the bound and angle are just harmonic oscillate around its equilibrium geometry. Then these four angles showing here are certainly not the equilibrium angle, right? So that means actually even for the parameters without any penalty, they could be different from the one that you would expect from the protocol. So even if you have a parameters that doesn't have any penalty, it is still a good idea to include all of them for optimization. So bottom line is, one's supposed to do more like reparameterize the whole ligand rather than just follow the literature, what is shown in the literature, that you only optimize the parameters with high penalty. That is probably, well, is probably a good suggestion, but um, if you look into this and then really try it, you will realize that it's not always a good suggestion. You just better take everything and then do it. And the real difficulty we encounter is actually how to do the dihedral potential fitting, because this part is not so often discussed in literature about the phase shift selection. So usually the dihedral in the Chang force field is represented in this form. So basically you have a periodic function, and this k is basically the well depth, and then the n is called multiplicity, which you can have a few multiplicity to describe one dihedral rotation. So this part is often used and often discussed in the literature. If there is any fitting is bad, people usually would just go to check the multiplicity and see if we are using the right one, and increase more and see if you can improve the potential fitting. And there is one extra parameter called, not extra, the last parameter called phase shift, which is usually taken as 0 or 180 in Chang force field. But this phase shift, how to determine it, is less discussed in the literature. So actually, we first try to add more multiplicities to improve our dihedral fitting, and hopefully that will help us to improve the MD simulation, but actually that did not work out. So then apparently the only thing we can try is to play with the phase shifts. But how? So this is the part which actually quite interesting. If you think about what the whole parameterization, the first step we do is try to find a global minimum of the structure. So that means we should try the structure we get is an energy minimum. So if we have to predict a dihedral phase shift, then at least we hope the structure, let's say we will hope to choose a phase shift such that the corresponding dihedral angle will locate in the potential minimum rather than maximum, right? So with this idea in mind, we go back to look at the parameters. So for instance, for this the first dihedral angle here, the predicted multiplicity n is 3, and the CGNFF actually predict a phase shift to be 0. So if you take n equal to 3, and then the phase shift to be 0, and then you can plot how the potential looks like, then you will find that, okay, its minimum potential appear at the 60 or 180 degree. However, the equilibrium dihedral angle is about 0. So what makes sense is to take the phase shift to be 180, such that your geometry equilibrium geometry will give you an angle that located at this potential energy minimum. So with this idea in mind, we then start to predict what is the phase shift supposed to be, and then we just keep it fixed during the optimization. So this is the way we do it, but usually before this, what people would do is either you can keep using the CGNFF phase, or you just let the FFTK to find it by the energy minimization. So we actually did all different way to see it for this one. So the first one, the first figure showing here is the potential energy scan from the content with the black curves. And the CGNFF means that we keep the phase the same as the CGNFF prediction. And FFTK means we let the FFTK to determine the phases through the optimization. And the optimized is we keep the phase the same as the prediction from the content geometry. So if you zoom in to see how the potential fitting, indeed you can see for the quantum one, it looks more like a proper well, while the CGNF and FFTK give you something like you have a peak, let's say the two legs standing, while the most important part, with the lowest energy part, it has a strange barrier, so that is definitely not right. But if you use the prediction and then keep the phase locked, then you can optimize the potential such that at least we can reproduce where is the equilibrium geometry supposed to be, or the energy minimum supposed to be, while maybe we lose a little bit for the how wide the distribution can be, but at least the they said the location of the distribution is at the right places. So with this these parameters, we can do the MD simulation, and indeed with this we can reproduce what is the major conformation. The major conformation from the MD simulation agrees very well with the quantum result. So MSD is just 0.02 Armstrong, and the other at least 0.2 Armstrong. So this actually just to show that getting the phase shift correct is really relevant for the for the dihedral potential fitting. And now we go back to our pinum, and then for the pinum, actually you can see this is the content and the optimized, basically based on the prediction. And of course we have a little bit off, so basically there is a dip that we couldn't reproduce it very well. So but it doesn't matter, because if we are what really important for us is actually to get the let's say minimum potential right. So in this case we basically reproduced the important geometry from the quantum as the quantum energy minimization will give. And then the interesting thing is we found that there is a second cluster. So the major cluster is the same as the quantum geometry, but the second cluster is a bit off. So basically you have a two dihedral angle. So basically this single bond and this single bond, they can rotate simultaneously. And once that occur, you can bring one conformation to the other. And this actually we also validated by doing a 2D dihedral scan to show how the quantum potential is like. So this is the quantum potential, and as you can see, this is the major conformation, and this is the minor conformation. So indeed, there is basically a potential valley that can bring you from one conformation to the other. And these kind of things in the 1D dihedral fitting, you basically can only see a dip. You don't find the real potential energy. They say the local minimum and another places, but you know that there is this kind of dip suggests that there is another conformation that is possible to be found somehow. So with this, I just to wrap up, what we learned from this is one should watch out for the parameters, even they are without penalties, and a dihedral phase shift should be determined based on the optimized geometry. And this is just a rule of thumb in cases that if you are also doing the potential energy, basically the parameterization of your ligand, then this is probably the first thing you wanted to try to fix your the phases before you do any dihedral parameterization. And if what didn't show you previously is if you encounter some cases that the equilibrium geometry give you an angle that is sort of in the middle of two possible phase shifts, then in that case, one should try different combinations and use the MD to do the MD simulation as, for the final parameterization to make the final decision. And with this, I wanted to thank my student, undergrad student Xia Songyan and Wu Qiyang. They basically participated in this project, and the funding from the Chinese University of Hong Kong at Shenzhen, and also the Shenzhen city government. Yeah, and thank you for your attention. I will be happy to take any question if